We will now move to a second more substantial talk by Professor Francesco Bullo, who, of course, remembers Elias also for the teaching, the guidance, and the support he received before he established his own credentials as a faculty member now at UC Santa Barbara.
Good morning or good afternoon, everybody. It's a great pleasure for me to be here today and have a chance to deliver this seminar at this memorial symposium in honor of Professor Emeritus Elias Masry. My name is Francesco Bullo. I'm a faculty at UC Santa Barbara, and I would like to talk to you today about some ideas on contraction theory and neural networks. So, Dr. Masry, I had a unique opportunity, pleasure, honor to meet him. I was a visiting student at UC San Diego, and during winter 1993, I had a chance to take his course on time series analysis and applications. And he was recommended to me by everybody I talked to, and he truly was a spectacular teacher. The course was challenging, exciting, was the best moment of the week. After that, he gave me a research problem. He was thoroughly a thoughtful research, careful. He was he generous collaborator, and later on we published, and then he helped me apply for graduate school, and he allowed me all of the information, help, support, afforded me that I needed at that time. So truly, in just a few months, he was, he had a major impact in my life, and I'm very thankful for that. And so that is why it is really a distinguished pleasure and honor for me to have this opportunity today to thank him again, to be able to speak about him to anybody who may know and honor his legacy. So since 93, my research has changed. Of course, I'm a control theoretician. I haven't had a chance to work on signal processing and time series analysis since then. And I would like to talk to you about just give you some ideas about some research work. I like to think he would enjoy it, since he was a theoretically minded researcher in the areas of signals and systems, just like I am, and just like this talk is about. Let me start by thanking my collaborators, my PhD student Alex Davidov, my former postdoc Saber Jafarpour, and my colleague Anton Proskornikov. And all of the content I described today is in various archive documents online right now. There is a beautiful subject of contraction theory for dynamics, for vector fields, for ordinary differential equations. These are all synonyms. Basically, a vector field is contracting if any two trajectories tend to converge to one another at a certain positive contraction rate c. And this theory works with respect to any arbitrary norm. So, for example, here I am visualizing a sup norm or infinity norm disk that looks like, of course, a square in 2 dimensions or a cube in higher dimensions. A vector field is contracting, therefore, if its flow is a contraction map in the sense of Banach. Talking about Banach, it was his stunning 1922 paper to begin this topic, even though there was some really interesting 1906 work also by Markov in the study of Markov chains, and based on very much a contraction idea. Among other examples. There is also a little known 1958 remarkable paper in Cyrillic by Lodzinski, and then that was so Banach work was 100 years ago. 50 years ago, a remarkable paper by Dissor and Haneda, making apparent how these tools are broadly applicable to exactly the type of problems that I will discuss today. Finally, at least in the area of controls, a landmark paper was in 98 by Lohmiller and Slotin. And by now, this area is well established. It's not a huge area, but it's a well established area in controls. These are 3 recent surveys that illustrate many applications and extensions of the theory. So one of the weaknesses of this area is that people have studied it under many different names. So for example, here in the slides, which you can find on you will be able to find on my website, here are 7 different references using 7 different names to characterize the properties of maps that are contracting. And I should say there is another equal number of conditions on the Jacobians of those maps, and one can show, as I will mention, that they're all equivalent. So one of the historical inconvenience of this area is that it has been studied under different names. But it is very remarkable in that the contracting properties has many useful implications in terms of both the transient and the asymptotic behavior of the ODE. Here are 4 of them having to do with the existence of equilibria or entrainment to periodic inputs under different assumptions, numerous robust stability properties. So actually, if any of you is interested in understanding robust stability for nonlinear dynamics, then clearly contraction theory is the way to go. A lot of interest, in fact early interest, was dedicated to these dynamics in the context of numerical integration with the work of Dahlquist and many others. But finally, what I would like to talk to you today is a topic that has received a little attention and that we've been exploring recently, and that is to say the use of contraction theory for ordinary differential equation to design and analyze fixed point problems. So the computation of fixed point of equations. So why am I interested in these fixed point problems? Well, because as argued by the 2 leaders of this field, the Combetz and Pesquet, fixed point strategies are very relevant in the modern data science. They provide a simplifying unified framework for modeling, analysis, and design of a number of optimization problems, Nash equilibria, monotone inclusion, dynamic programming, and so on and so forth. Let me tell you about the specific example that I wish to come back to at the end of this talk. As you're all familiar with, we live in the world of feed-forward neural networks. Over the last 10 years, there has been an explosion of interest in deep networks and their ability to practically solve a number of regression, clustering, supervised and unsupervised learning problems. So today I'm going to talk to you about a paradigm that has received only recently attention, and that is that of using implicit models to solve supervised learning setups, and implicit architectures to solve supervised learning and unsupervised learning problems. In implicit architecture, the point is that instead of having layers where you go from xi to xi plus 1, you set up a single large layer, perhaps, dimensionality I'm not going to talk about today, but you set up a single layer, and this layer, in order for the solution to be computed, you need to solve a fixed point problem. It's easy to see that the implicit model is a superset of the feed-forward model. It's also easy to see, as I'll show a little bit better later, that this fixed point equation is associated to a continuous time differential equation that is typically studied in the context of continuous time recurrent neural networks. So that's why I have implicit / recurrent here. Another name that people have been using is that of equilibrium, deep equilibrium models. It's all similar: implicit neural networks, equilibrium models, fixed point networks, they're all the same. The key point is, before I proceed, is why is this new class of neural networks receiving attention lately? And that is because of a number of reasons listed here, including simplicity in the formulation, analogy with biological neural circuits where feedbacks, skip, and equilibrium connections are common. And then ultimately, as is of utmost requirement in machine learning, is accuracy in the ability of solving a learning problem. Memory efficient is another reason. Back propagation can be implemented more efficiently. And one of the properties that is very close to my heart that I'll briefly mention is input-output robustness. So recent empirical results demonstrate that implicit neural networks have the potential to have many advantages over feed-forward neural networks. The science of why that's true is only being currently scratched. Now, in these slides, which will be on my website, you can find references about most the literature, both the recent about implicit neural networks as well as the literature on continuous time recurrent neural networks and how they connect. All right, so here's the fixed point problem that I wish to solve, and you're all familiar with the Banach contraction theorem, which tells you that if you consider this simple iteration, which we'll call the Picard iteration, then this iteration is a Banach contraction map, and many good properties are satisfied if the Lipschitz constant of the map is less than 1. What happens when the Lipschitz constant of the map is greater than 1? Perhaps precisely because you are designing an architecture and you want the architecture to be imposing as limited requirements as possible on the parameters. So you want to look over a large parameter space. So now, if the Lipschitz constant is greater than 1, then one idea, a very simple idea, is to study not the Picard iteration, but actually consider the Mankrasinski iteration that I will refer to as the damped or average iteration in what follows. So basically you slow down the iteration. That's all you need to do. And now the question is, what is your step size alpha? And when does this work? Why is this useful? All right, so while the Banach contraction theorem is very widely known, the following theorem may not be, and maybe, well, to me it was relatively surprising. And this is a theorem, part of which is known in the literature of monotone operator and part of which we have generalized lately. It tells you that if you're interested in the average iteration, the average iteration is Banach contraction. When you can find an alpha less than 1 that makes it work, right? So that this property 1 is if and only if, so these are 3 necessary sufficient equivalent conditions. The map G has a one-sided Lipschitz constant less than 1. So you're not interested in Lipschitz constant, now you're interested in one-sided Lipschitz constant, which I will review in a few minutes. But in terms of dynamics, you are now saying that the ODE x dot equal to minus x plus g. So basically here I'm defining a map f equal to minus identity map plus g, so it's just a translation of g. That particular ODE is contracting, is infinitesimally contracting in the sense that I've been showing and talking to you for the last several minutes. So the importance of this theorem is that if you're interested in understanding when can you use this discrete time algorithm, then this is if and only if the ODE is infinitesimally contracting. So there is a deep connection, and understanding the ODE is helpful to obtaining fast convergence rates and understanding optimal step sizes for the average damped Mankrasinski iteration. So that's the point. That's the key point. That's why I want to design a discrete time algorithm, but in order to do that, I am actually studying ODEs at some level. All right, I mentioned to you that robustness in the input-output map is very important. So what is the input-output map meaning here? It means that now I am not working any longer with a fixed point problem, but with a perturbed fixed point problem. There is an input signal u, constant in this case. These are all time invariant problems. There's time-dependent versions, but I'm not going to talk about them today. And as you change the value of u from u to v, and there is a distance that you change in the input, so by how much is the input perturbed, then the perturbation in the fixed point is upper bounded by a constant highlighted here in this circle. This is known as the Lim's lemma in fixed point theory, but there is an extension of it, an improvement of it, because this constant here that I am highlighting in the second box is necessarily smaller than, or at the most equal to, the constant in the old Lim's lemma. So the one-sided Lim's lemma gives you better bounds. And in general, this is now telling you that not only can I design a discrete time algorithm by studying the continuous time ODE, but also I can talk about its robustness properties. So I'll skip the background on the proof, but that's available on my website. So now what was that one-sided Lipschitz constant? Let me do it first in the case of scalar functions, just scalar functions. So basically, one-sided means you just take an upper bound on the derivative, not an upper and lower bound. It's not a bound on the norm of the derivative, it's just an upper bound on the derivative. So the upper bound on the norm needs to be non-negative, but an upper bound on the value of the derivative can also be negative. It's easy to see that this upper bound on f prime can be written in this inner product quadratic form, like where it's x minus y into fx minus fy, upper bounded by a quadratic function of x minus y. The second expression is the one that it's easy to generalize to multivariable calculus. So, little observations. If the one-sided Lipschitz constant is 0, then the function is the same as saying that the function is weakly decreasing. If f is Lipschitz with the bound L, then it's also SL with the constant b that is upper bounded by L. So perhaps it's smaller than L. And it could well be negative. If the function is strictly decreasing, then the one-sided Lipschitz constant is strictly negative. And also let me remind you, there is a basic tool in the study of differential equation called the Gronwall comparison lemma, whereby if you have an upper bound on f prime, then in fact you get an upper bound on the distance between two trajectories, and that's what we wanted. That's what we wanted. So let me now give you 4 slides on what is the standard theory in Euclidean space. I'll do it quickly. I don't want to spend too much time. The first result, slide number 1, is a fundamental equivalence that exists between a map F being one-sided Lipschitz and having a constant minus c, where c is positive. That's given by condition number 1. So a map like that is a one-sided Lipschitz, and it has a constant of minus c where c is positive, and it's referred to as the contraction rate. Condition 1 is if and only if with a linear matrix inequality on the Jacobian of the map F. So this is the standard theory. The standard theory is expressed with respect to the, let's call it standard L2 norm with a weight described by a positive semi-definite matrix P. And so this LMI has to be satisfied everywhere at condition 2. This is also called the classic Krasovsky condition on the vector field F. Finally, this is if and only if, just like we just mentioned the Gronwall lemma, with an incremental stability condition, a differential incremental stability condition. Incremental stability talks about the distance between two trajectories. It's not the distance from one trajectory and an equilibrium point. Between two trajectories, that's referred to as an incremental stability, and it's a differential condition because here on the left-hand side I have a Dini derivative. So this is a differential condition. So in the standard contraction theory, on an inner product space, you have these 3 equivalences. And the problem with these 3 equivalences is they do not very nicely apply in a very efficient manner on the implicit neural network problem that I want to analyze. So I will work on that. But let me first tell you this theory. This theory comes with multiple additional properties. For example, it is well known that a strongly contracting vector field is closely related to functions that are strongly convex. And it is well known that if the vector field is strongly contracting, minus f is a monotone operator or recursive operator in a monotone operator theory. So basically this contraction theory is closely related to convex optimization and monotone operators. In some sense, it's a transcription of those theories to ordinary differential equations. It should come as no surprise that when a vector field is strongly contracting, then its flow is a contraction, just like in my very first picture. There exists a unique equilibrium globally exponentially stable, and it comes with multiple Lyapunov functions that are very intuitive and helpful. Finally, from the field of monotone operators, one gets the following results. One that gets that results that I was telling you earlier about, that if and only if, the infinitesimal contraction. So if you have a 0 problem for f, which is the same as a fixed problem for g, then the average iteration for g becomes the Euler integration for f as a vector field, or the forward step as a monotone operator for f, which bottom line is this same algorithm right there. So now, with this translation and understanding, the theorem is the following. If I have a contraction rate, contraction rate C, ellipsis constant L, then it's well known for what ranges of values of alpha is the average iteration and contraction, and it's well known what is the optimal step size and what is the minimum, the corresponding optimal, which is minimum contraction factor. So this is well known in Euclidean space, in inner product spaces. Some of this is also understood for Hilbert spaces. But for our implicit neural network problem, it is convenient to use a generalization of this theory to non-Euclidean norms, because it is easier for non-Euclidean norms to establish the contractivity of the vector field. So the full theory includes some results on the case of Riemannian manifolds, which I will skip. This beautiful new theory that is being developed right now talks about the fact that if I am using the standard Euclidean norm, I have available an inner product and I have available an LMI, a linear matrix inequality. If I want to generalize this theory to arbitrary norms, then I need to introduce appropriate operations. One set of such operations is referred to as weak pairing, specifically the mean and the sign and the max pairing. These are pairing that are very useful, as I'll mention in a second, that play together nicely with the 1 and infinity norm. And also, instead of having LMIs, one introduces the operation of logarithmic norm of a matrix. There's a beautiful theory of logarithmic norms and weak pairings. I'm not going to spend too much detail. There's beautiful properties. Weak pairings are the weaker versions of inner product. They are closely related to a norm in the sense that, and let me enlarge it here, as you see, if you have a norm of a signal, the time derivative of that norm leads directly to the definition of the weak pairing. Weak pairing and log norms are closely related through this identity, this quadratic identity. And log norms, there's a classic literature about log norms. They're convex operators. They're generalization of norm, induced norm for matrices with a beautiful history. The point is here, let me wrap up my talk, is that in this new theory, we are able to re-establish the equivalence between these three conditions. I showed them to you earlier for the Euclidean case. Now we are able to establish them for arbitrary norms with appropriate log norms and compatible weak pairing with appropriate properties. And so these three conditions, I don't want to spend the time now, but they are really one-to-one, very close correspondence with the conditions I showed earlier. Earlier there was an inner product between x minus y into fx minus fy. Here it's a weak pairing, which is a corresponding operation. Earlier we were asking for an LMI to be satisfied for a certain value of c. Now we're asking for a log norm of the Jacobian to be upper bounded by minus c. In both cases, the differential incremental stability condition is actually, in this particular formula, is entirely identical to before. And then there is an entirely equivalent, this was the fourth result, right? There's an entire equivalent fourth result for now the non-Euclidean case. And it tells you that the average iteration of G or the forward step method for F are contraction under some assumptions. Specifically, there is a range of values of alpha for which they are contracting. This range depends upon the contraction rate, the Lipschitz constant, just like before, or if one wants, it's elegant to express them as a function of the condition number, the ratio between Lipschitz constant and contraction rate. And there are expressions for the optimal step size and corresponding minimum contraction factor that are rather similar to the ones before. In fact, in the papers, there's further simplifications, which I don't want to review. So the theory generalizes very nicely to the non-Euclidean case, whereby by non-Euclidean I mean to say with respect to the L1, L infinity or subnorm. So, and the weighted cases as well. Bottom line, allow me now to come back to the problem that I started with. I was interested in discussing a fixed point problem of the form x equal to phi of ax plus bu, and there is also an output equation which is irrelevant at this time. So we have a neural network problem and a supervised learning problem. For example, I have an input-output map, I have data, and I postulate the adoption of this architecture. And now I want to make sure that I have a good way of ensuring that a unique equilibrium and unique fixed point of this formula exists. And I need to tell you how to compute it, as well as want to study its sensitivity to changes in the inputs, which is the robustness of it. Now, this iteration, this fixed point problem is inherently tightly connected with a certain ODE and with a certain algorithm. This ODE is actually itself a standard model in the study of recurrent neural dynamics. This is referred to as the firing rate model. It's really just like a transpose of the Hopfield neural network dynamics. Hopfield introduced in 1982, so there's a beautiful history about these ordinary differential equations. And the Euler step for this equation, which is the average Krasnodębski-Mann iteration of the fixed point problem, is the average iteration here is given by this particular algorithm up there. And the question is, what alpha do you want to use? And is it true that a unique equilibrium exists? So the theory that I have just exposed to you gives you the following answers. The model here, the new implicit neural network model, is well posed, meaning to say a unique solution exists, if the log norm of the A matrix is less than 1. By the way, this log norm condition is just a diagonal dominance condition. This log norm condition is less conservative than the induced norm of A. So if you were to use that, it would restrict unduly the coefficients allowable in the synaptic matrix A. And then, with respect to the sup norm, the infinity norm, my firing rate dynamics is contracting with a certain rate, and based on the theory that I've shown to you, there is a natural expression for the optimal step size and for the corresponding minimum contraction factor. And as of date, these are the best numerical results, lead to the best numerical results for these classes of problems. I'm not going to show you the details of the input-output bounds, nor am I going to show you the details of how you do the training for the implicit network and the empirical results. They're all in the new RIPS paper. In summary, my talk can be summarized. What I've done is I've shown you some connections between contraction theory, monotone operator theory, and neural networks, of course, right? And I've tried to bring together ideas from control, optimization, and learning problems. I've shown you what's known in the Euclidean case and how to extend it to the non-Euclidean. There are beautiful questions on the case of Riemannian manifolds that are not yet answered. All right, I would like to conclude my talk by again dedicating it to the memory and the legacy of Dr. Elias Masry. I was fortunate to have him, to have a chance to meet him when I was an education abroad student in '93. I had a chance to meet him, as I mentioned earlier. He was the first to teach me an exciting, challenging graduate course. The first to actually, before accepting me in the graduate course, he looked me in the eye and he told me, "Francesco, this is going to be very hard. I don't think you can take my course. Show me you can do it." That was an example of tough love that I totally loved and motivated me for a long time later. So he was the first to give me some tough love, which I needed, to teach me a great course, to offer me an independent study, to give me an open research project, to supervise me around the complexity of it and finishing it. He was my first conference paper co-author, my first journal paper co-author. He was the first to tell me I should go into academia. One day he told me, "Francesco, you should consider a career in academia." I remember not knowing what that meant at the time, and here I am, 30 years later, 29 years later. He gave me a lot of help in getting into grad school and understanding, coming back to the US. And so truly, I don't know what word to use rather than to say that he really, to me, in just a few months, was truly a marvelous mentor. And the best I can aspire to do is do the same to my graduate students right now. So with that, thank you all, and I hope I have a chance to meet you all in person one of these years at some point in time. Thank you again.
Thank you very much, Professor Bullo. I think this is a memorial for Professor Masry, but it's also a celebration of what deep theoretical work can do. On that context, I wanted to recognize and draw attention to the fact that you've served as department chair, you've served as the president of the IEEE's Control System Society, and a similar leadership role at SIAM. You've been recognized for your efforts as fellow of the IEEE, the International Federation of Automatic Control, and SIAM. So it's impressive to see how rigorous work doesn't sit in isolation, but goes on to make an impact in so many different ways. I wanted to invite you to share any additional thoughts that you might want to share with the audience that gathered here
Yeah,
today.
thank you, Dr. Rao. Thank you so much for the invitation. I was really just, you know, one of those visiting students who's lost and doesn't really quite know what he's up to, what his life like, and what I was supposed to do with my life. And Dr. Masry, you know, as I mentioned, welcoming me into his office and told me, "You're just an undergraduate student. I don't think you. Are you sure? I don't think you'll be able to take my course." And I really benefited from that. And then right. And then the rest, as I mentioned, he in just the space of a very few months, he taught me so much, you know, in all aspects of academia. I also want to, I didn't mention it in neither in my talk, but I had the same experience as Dr. Moda mentioned. His rigorous thinking and he's not backing down from a challenge. Our paper received, you know, the usual you know, distracted reviews along the lines of, yes, this is right, but we're going to reject it. And I remember seeing his communications with the associate editor, at the end of which the paper, sure enough, did appear in the transaction on information theory. So that was inspiring to see him. I remember just serendipitous luck at the time. He visited my hometown of Padua as my visiting period had finished, and we met in Padua, and I was showing him the town. We went into the historic old square, and there was a famous clock tower. He took a picture in the morning. We continued walking around throughout the day. We walked back into the square, and he took a second picture of the same clock tower. And he then looked at me. I was a bit puzzled and surprised. Why would you want to take a second picture of the same building? And he explained to me, now nobody can doubt that I am interested in time series. So that he said to me in '93, and I very much remember that very, very clearly as of today. Right. We had discussions about the virtues of LaTeX versus Prof. For those of you who are familiar with software to render mathematical equations. And I was told that LaTeX uses too many curly brackets to be, you know, of his taste. As I mentioned, I was, and I still am at the time, I was interested in control theory. So my advisor back in Italy. So I continued on to a PhD in controls, but he was incredibly gracious and supportive. He guided me throughout the entire PhD application process. He helped me understand, you know, whom to. I remember him sitting down with me and evaluating different possible advisors for me as a graduate student in a different area. And I have to admit that over the years I've been trying to look for him in a very distracted way. I wish I had a chance to see him again. I visited San Diego once, and I had a chance to meet with him, and he was still in full force. And I remember a meeting with a controls professor, shall remain nameless, but I had a distinct impression that the young control professor was rather intimidated by Professor Masry in his full strength and vision and influence. And And but nevertheless, I am looking back and rethinking about those years. It is clear in my mind that he had a huge, huge impact and set me on the path that has taken me to where I am right now. So I am deeply grateful, and I am right. I'm very happy to dedicate this little talk to his honor and in his legacy. Thank you, Dr. Rao.
Thank you so much, Professor Bullo. Much appreciated. I remember little micro projects of my own, swapping LaTeX macros with him. I know exactly what you mean. Thank you again. So, talking about control theorists, we have a testimonial here from Professor Bob Bitmead, who notes what an eminent scholar Elias was and how welcoming he was and accommodating he was when Bob Bitmead arrived at UCSD back in 1999. I recall sitting on doctoral committees with him and appreciating his insights and views. I found him both humble and superbly expert in the field of systems and signals, notably stochastic systems and time series. Like all of us, saddened by the loss